Welcome to G Fun Facts Online. Today, we're diving into a world so fast it makes a lightning strike look like it's moving in slow motion. We're talking about the realm of femtoseconds. What's a femtosecond? It's a quadrillionth of a second. That number is so ridiculously small, it's hard to wrap your head around. So let's try this. A femtosecond is to 1 second what 1 second is to about 31.7 million years. Imagine being able to pause time, not for a day, not for an hour, but for a single femtosecond. In that frozen moment, you could watch the fundamental dance of the universe, the interactions of electrons and atoms that create everything we see and touch. This isn't science fiction. This is the world of ultra-short pulse lasers, the tools that are allowing scientists to witness and control matter in its most chaotic and fleeting states. In the physical world, things are almost never truly at rest. Atoms are constantly jiggling, vibrating, and interacting. But what happens if you shatter this delicate balance? Not with a gentle nudge, but with an explosive blast of energy, delivered in a time frame that is almost incomprehensibly short. You create a state of matter that is completely out of whack, a non-equilibrium state that exists for mere picoseconds or femtoseconds, yet holds the secrets to creating the materials of tomorrow. The heart of this revolution is the ultra-short pulse laser. These aren't the laser pointers you use to play with your cat. These are marvels of optical engineering that emit bursts of light that last for just a few femtoseconds. The journey to create these incredible tools began back in the 1960s, shortly after the first laser was invented. Early breakthroughs like Q-switching and mode locking helped shorten laser pulses from milliseconds down to nanoseconds and picoseconds. But the real game changer arrived in the 1980s with a Nobel Prize-winning invention called chirped pulse amplification, or CPA. Developed by Gerard Mourou and Donna Strickland, CPA solved a huge problem. How do you make an ultra-short pulse incredibly powerful without it destroying the very equipment you're using to amplify it? The solution was pure genius. First, you take a short, weak laser pulse and stretch it out in time, making it much longer. This reduces its peak power, so you can safely feed it into an amplifier and crank up its total energy. Once it's been amplified, you do the reverse. You use a set of gratings to compress the pulse back down to its original, ultra-short duration. All that amplified energy is now squeezed into a tiny sliver of time, creating a pulse with an absolutely staggering peak power, often reaching into the terawatt or even petawatt range. A single petawatt pulse can be more powerful than all the world's power plants combined, but only for a fraction of a second. It's this immense power, concentrated into a femtosecond burst, that allows these lasers to interact with matter in such a unique and powerful way. So what happens when one of these ridiculously powerful, unbelievably short laser pulses hits a material? This is where things get truly weird and wonderful. In our normal, everyday experience, when you heat something up, you're giving energy to its atoms, making them vibrate more and more until the material melts or changes in some way. But a femtosecond laser pulse is so fast that it doesn't play by these rules. When the pulse strikes, its energy is absorbed almost entirely by the electrons in the material. This happens on a timescale that is much, much shorter than the time it takes for these excited electrons to transfer their energy to the atoms. This creates a bizarre, highly unstable state of non-equilibrium. Imagine a city where, in an instant, every single person starts running around at supersonic speeds, while the buildings, the cars, and the streets remain perfectly still and ice cold. That's what happens inside the material. The electrons can be heated to tens of thousands of degrees Celsius, hotter than the surface of the sun, while the atomic lattice, the buildings of the material, remains close to room temperature. This idea is so central to the field that it has its own name, the two-temperature model. It treats the electrons and the atoms as two separate systems, each with its own temperature. There's T, the super hot temperature of the electrons, and TL, the cold temperature of the lattice. For a brief moment, these two systems exist at drastically different temperatures, and the model describes how the energy eventually flows from the hot electrons to the cold atoms. The consequences of creating this two-temperature state are profound and lead to phenomena that seem to defy common sense. One of the most mind-bending is something called non-thermal melting. As you can guess from the name, this is melting that happens without heat in the traditional sense. In certain materials, especially semiconductors like silicon, the intense electronic excitation caused by the laser pulse can weaken the chemical bonds holding the atoms together so much that the entire crystal structure destabilizes and collapses. It literally falls apart on a sub-picosecond timescale. The atoms don't have time to get hot and vibrate themselves into a liquid state. Instead, the very glue holding them together dissolves, and the solid simply ceases to be a solid. It's a fundamentally different way of melting something. This process of extreme heating and subsequent, incredibly rapid cooling, at rates exceeding 1 trillion degrees Kelvin per second, can also be used to forge new materials. You can essentially freeze the material into a structural arrangement that wouldn't be stable under normal conditions. This is called a metastable phase. It's like flash freezing a chemical reaction halfway through. This opens up a whole new toolbox for materials science, allowing us to create entirely new materials with novel properties that might be impossible to make any other way. There are also more practical applications. Because the laser pulse is shorter than the time it takes for heat to spread, these lasers can remove material with incredible precision. This is called cold ablation. It can carve and machine materials, even delicate ones, with almost no collateral damage, no melting, and no charring around the edges. It's the ultimate surgical scalpel for materials, used in everything from high-precision manufacturing of medical devices to delicate eye surgery. Okay, so we can create these fleeting, chaotic states. But how on earth do we see what's happening in a process that's over in the blink of a femtosecond? This requires experimental techniques with equally impressive time resolution. The workhorse of this field is a beautifully simple concept called pump-probe spectroscopy. Think of it like setting up the world's fastest camera. You use 2 laser pulses. The first is a strong pump pulse. This is the one that strikes the material and initiates all the chaos, creating the non-equilibrium state. Then, after a very precise controllable time delay, you send in a much weaker probe pulse. This probe pulse acts as your camera flash, measuring the properties of the material at that exact instant. It might measure how much light is reflected or transmitted, or something more complex. By repeating this process over and over, each time changing the delay between the pump and the probe just a tiny bit, a few femtoseconds at a time, you can build up a series of snapshots. When you string these snapshots together, you get a stop-motion movie of how the material's properties evolve as it goes from chaos back to order. Scientists have developed several different types of these pump-probe cameras, each designed to look at a different aspect of the process. The simplest is optical pump probe, which just looks at changes in reflectivity. This tells you a lot about what the sea of hot electrons is doing. For a more direct look, there's a powerful technique with a very long name: time-resolved angle-resolved photoemission spectroscopy, or TRARPS for short. In a TRARPES experiment, the probe pulse is a high-energy ultraviolet or X-ray pulse. It has enough energy to literally kick electrons right out of the material. By measuring the energy and angle of these ejected electrons, scientists can reconstruct a direct picture of the material's electronic structure and see exactly how it's being warped and changed by the pump pulse. It's like getting a direct data feed from the electron chaos. But what about the atoms? Optical techniques only give you indirect information about the atomic structure. To actually see the atoms moving, you need different probes. This is where ultrafast electron diffraction and time-resolved X-ray diffraction come in. In these experiments, the probe isn't a pulse of light, but a short pulse of electrons or X-rays. Just like light, electrons and X-rays can diffract off a crystal lattice, creating a pattern that is a direct fingerprint of the atomic arrangement. By recording these diffraction patterns at different time delays after the pump pulse hits, you can literally watch the crystal lattice bend, vibrate, and even melt in real time. These techniques have been crucial in providing the direct, smoking gun evidence for non-thermal melting. Of course, the way a material responds to an ultrashort laser pulse depends heavily on what kind of material it is. In metals, you have a sea of free electrons just waiting to absorb energy. The laser pulse hits, and you instantly get a, quote, hot electron soup. The energy then slowly, on a picosecond timescale, leaks from the hot electrons to the cold atomic lattice. Semiconductors, like the silicon in computer chips, are an even more fascinating playground. Here, the laser energy creates pairs of electrons and holes, and as we discussed, if you create enough of them, you can trigger non-thermal melting. But you can also do something else incredible. The impulsive kick from the laser can launch coherent phonons, which means all the atoms in the crystal lattice start vibrating together in a collective in-phase motion. Imagine a stadium full of people, all doing the wave perfectly in sync. That's what a coherent phonon is, but with atoms. Observing these atomic dances gives us a huge amount of information about the fundamental interactions within the material. Then you have insulators and dielectrics, like glass. These materials are normally transparent because they have a large energy gap that electrons can't easily cross. But the extreme intensity of an ultrashort laser pulse can force the issue through processes like multiphoton ionization, where an electron absorbs several photons at once to make the jump. This can rapidly create a dense plasma of electrons inside the transparent material, transforming it into a highly absorbing, metallic-like state for a few brief femtoseconds. Understanding all this mayhem requires more than just experiments. Scientists rely on powerful theoretical models and computer simulations to make sense of their observations. The two-temperature model is a great starting point, but for a more detailed picture, they use things like the Boltzmann transport equation, which doesn't assume the electrons are in a nice, simple thermal state. They also use molecular dynamics simulations, which model the motion of every single atom, giving an atomistic view of processes like melting. And at the highest level, there are ab initio, or first principles calculations based on quantum mechanics, which try to predict the material's behavior from the ground up, with no guesswork. So where is all this heading? The field of ultrashort laser science is still young, and the future is incredibly exciting. Scientists are pushing to create even shorter laser pulses, entering the attosecond regime. An attosecond is a billionth of a second. On these timescales, you could watch the motion of electrons within a single atom, before the atom itself has even had time to move. But the ultimate goal isn't just to watch, it's to control. A deeper understanding of these non-equilibrium phenomena could allow us to use light to control material properties on demand. Imagine flipping a switch that uses a pulse of light to turn a material from an insulator into a metal, and back again, creating the basis for electronics that are millions of times faster than what we have today. Or using precisely sculpted laser pulses to act as photonic catalysts, driving chemical reactions along specific pathways to create new molecules. By combining these amazing lasers with next-generation tools like X-ray free electron lasers, we'll gain an unprecedented view into this ultra-fast world. And as the amount of data we generate explodes, machine learning and AI will become essential partners, helping us to analyze complex results and perhaps even discover new physical principles hidden within the chaos. From building better electronics and creating supermaterials to performing impossibly precise surgery, the study of what happens in these fleeting moments is already changing our world. By shining an unimaginably fast and powerful light on matter, scientists are not just observing the fundamental dance of atoms and electrons. They are learning the steps, so that one day they can lead the dance themselves. They are learning how to manipulate the building blocks of our universe, opening the door to a future where we can design and create materials with properties that were once purely the stuff of science fiction. These fleeting moments of chaos, lasting less than a trillionth of a second, are truly forging our future. Thanks for tuning in to G Fun Facts Online.